Okay, so in this section, section 5.2, we're going to take a look at transforming and combining random variables. So all that means is that's basically like saying we're going to add or subtract numbers to our distributions, our probability distributions. And hopefully this shouldn't be too bad because this is something that we did back in Unit 2 with our normal distribution. So what you're going to be able to do is to describe the effects of a transformation on a random variable. So basically like taking a probability distribution table or histogram and adding or subtracting a constant to it and multiplying and dividing by a constant. So what happens if we add or subtract, multiply or divide, find the mean and standard deviation of the sum or differences of independent random variables. So basically if I add two random variables together and make one new distribution, what's the new mean and new standard deviation? And find the probabilities involving the sum or differences of independent normal random variables. And we'll go through each of these in this section and hopefully they won't be too bad since we've done a lot of this in previous units. Okay, so like I said, we did some of this in chapter 2. So we're going to take a look at some linear transformations. So in section 5.1, we learned about the mean and standard deviation. They gave us important information about the random variable, the center and the spread of the distribution. So in this section, what we're going to look at is we're going to take a look at how the center and the spread of the standard deviation are affected by transformations on random variables. So what happens if we add something to our random variable, subtract something, multiply, divide? But you've done this before. So in chapter 2, we took a look at the effects of linear transformations on the shape, center, and spread of the normal distribution of data. So just as a quick reference, remember when we added or subtracted a constant to each observation, what it did was, let's say that we were looking at the average number of minutes that we spend on the internet. If we added a number, we said, oh, we underestimated it, we need to add 50 minutes to every observation. All that did was it added 50 minutes to the mean because I took that original mean, let's say the original mean was 20 minutes and I added 50, just moved it down the number line to 70. Okay, so when we add something, it's literally just moving it down the number line. It didn't change the shape or the measure of spread because it's basically taking my whole histogram, physically picking up and moving it down. When we multiplied or divided each observation by a constant, remember that it multiplies or divides the measure of center by b. So if I took it and I said, oh no, we did twice as many minutes as we needed to and the mean was 20, if I just would divide that mean by 20 by 2 and that would give me a mean of 10. It also multiplies or divides the measure of spread. So when we multiply or divide by a constant, it does change the spread. It either makes it more spread out or less spread out. So you want to multiply or divide your standard deviation by the measure of the constant that we multiplied or divided by, but it still doesn't change the shape of the distribution. So when I say shape, that means it doesn't go from being approximately normally distributed to skewed right or skewed left. All right, so we're going to take a look at how these transformations are applied to probability distributions of random variables. How are they affected by similar transformations? So the first example we're going to take a look at is at multiplying a random variable x and see how this changes the mean and standard deviation. Hopefully you'll see that it does the same thing to our random variable x that it did in our normal distributions back in Unit 2. All right, so let's just take a look at some Jeep tours. Pete's Jeep Tours offers a popular half-day trip in a tourist area. So we're going to Fiji, we're going to get or Hawaii, we're getting a Jeep tour, okay? So there must be at least 2 passengers for the trip to run, and the vehicle can hold up to 6 passengers. So we're defining X as the number of passengers that will go on a randomly selected day. Make sure, once again, that you're still defining what your random variable X is going to be. So here's the number of passengers. We can hold 2, 3, 4, 5, or 6. This is discrete. All right, it's discrete because I can't take 2.5 passengers. And what's the probability that I have 2, 3, 4, 5, or 6 passengers are represented at the bottom of the table? Remember, your histogram is always the number of passengers, and the horizontal axis is always going to be the probability of each occurring. All right, so we can take a look, we can figure out what the mean is. Remember, the mean, multiply and then add, multiply and then add, multiply and add, multiply and add, multiply and add. Okay, the mean of x is 3.75, so that's your average. And the standard deviation is 1.090. Remember, you can get that from your graphing calculator. If you need to do a refresher of the formula from the previous section, go for it. So here's what we know. So this is our original distribution. We know that he charges $150 per passenger. Must be a pretty good tour, right? The random variable C, okay, now we have a new, I'm not defining it as X because it's C because I'm changing something. The random variable C describes the amount Pete collects on a randomly selected day. So all we're doing is we're saying, okay, so instead of the X value being how many passengers, now it's how much we've collected. So if we have 2 passengers, multiply that by 150, we get 300. 3 passengers multiplied by 150 per passenger is 450, 4 times 150, 600, so on and so forth. Okay, now if I were to take the amount of money that I've collected and the probability of getting each amount of dollars or money on that particular day, what would my histogram look like? Okay, well, actually, if you take a look at them, they look pretty similar, right? The only thing that's changed, notice, is my x-axis. It went from the number of passengers to the amount of money that I've collected, but the probability stays the same because if I have 2 passengers, 15% chance of having 2 passengers, that means I still only have a 15% chance of collecting $300. So they look very similar. The only thing that's changed is my x-axis. The mean in this case, okay, if you take a look at this, since my x-axis has changed, is $562, so right here, and the standard deviation is 163.50. So what we're going to do on the next couple of slides is compare the shape, center, and spread of these two probability distributions. Now you should notice, well, obviously the mean has to change because these numbers are a lot bigger. That also means the standard deviation is going to change because I've moved it down the number scale. All right, so let's just take a look at the mean and standard deviation and see how they changed. Here's was our original. What did we do? We multiplied it by a constant of 150, all right? And I have my new histogram over here. So look at the mean, 3.75. 562.50. Well, how did I go from 3.75 to 562.50? Think about it this way, if the mean number of passengers that I get is 375, what's the average cost going to be? Well, the average cost is going to be 375 times 150 to give me, on average, I'm going to earn $562.50 a day. If the standard deviation was 1.090 people, okay, I can either have 1.090 people above the mean or below the mean. How much money is that going to change per day? So if this is the amount of people, how can I figure that out? If I multiply it by 150, that's saying, well, if it could deviate from the mean by about 1 person, that means that the amount of money that's going to deviate from the mean is also multiplied by 150 to get it in dollar form, which gives you 163.50. Okay, so we took the old mean, 375, multiplied it by 150 to get the new mean, the old standard deviation, multiplied it by 150 to get the new standard deviation. All right, so multiply by a constant, all you do is multiply the old mean, old standard deviation to get your new mean, new standard deviation. All right, so let's compare the shape, the center, and spread of the two probability distributions when I multiply it by 150. Okay, take a look at the two shapes. The shapes are exactly the same. They're both approximately normally distributed. So when I multiply by a constant, it doesn't change what the shape looks like. Still normal. Didn't make it skewed right, skewed left, nothing crazy. The mean of X was 375 and the or $3.75 people, and the mean of my new standard mean of my new graph of the amount of money that I collected was $562.50, which means if you take a look at this notation here, mean of C, that's saying the mean of the cost, is 150 times the mean of the number of passengers. So it's basically like saying to get the cost, you take the number of passengers times the cost per person to get your new mean. Now, how about the spread? The spread of the number of passengers was 1.090. The standard deviation for the cost is 163.50. That means that the standard deviation of the cost is $150 times the standard deviation for the number of people. So if the number of people vary by 1.090, if I multiply that by $150 per person, gives me my new standard deviation. Okay, so Here's just a general overview of what happens when you multiply a random variable by a constant. So if you multiply a random variable by a constant to get the new measure of center, all you're going to do is take the old mean, multiply it by the transformation, gives you the new mean. All right, for the standard deviation, same thing. Take the old standard deviation, multiply it by the constant, get the new standard deviation. So the measures of spread, the range, the IQR, and the standard deviation all do the same thing. They all get multiplied by that constant. Remember, didn't change the shape, still approximately normal, not going to make it skewed right or left, okay? So as with data, if we multiply a random variable by a negative constant, okay, so this is the tricky part. So let's say we multiplied by a negative constant. Just remember that your spread is just going to be multiplied always by the absolute value, because our measure of spread is always a positive number. It's never a negative number. And then we just talk about the direction, above the mean or below the mean. Okay, so let's just take a look at what happens when we add a constant to a random variable. So let's take a look at Pete's Jeep tours again. All right, going on some tour of Hawaii or Fiji or somewhere. So we're taking a look at the cost that we have collected. All right, so how much money is he going to make or collect each day by giving his Jeep tours? So it costs Pete $100 per trip to buy permits, gas, and a ferry pass. The random variable V describes the profit he makes on a randomly selected day. So this is how much money he's collected, $300, but it costs him $100 each time. So what we're doing is we're subtracting $100 to get the new data point. So 450, but he has to pay $100, so he only is making 350. Same with each of the other two. We're subtracting 100 to show how much profit he's actually going to make. Let's take a look and see what that new distribution looks like. Oh, let's take a look at this. Notice we still have exactly the same shape. They didn't change, but just look at my number scale here. All right, so money collected, all right, goes from 150 to 900. The profit is how much money he's actually making to, he can spend on whatever he wants. It's from 200 to 800. So really the x-axis just changed. All right, we're going to see what that means. Take a look at this mean. The mean is 462 and the standard deviation is still 163.50. So we're going to compare the shape, the center, and spread of what happens when we add or subtract a constant to my distributions. All right, so what happens to the mean? So first of all, I took all of my data points and I just subtracted 100 from them, then plotted the probability distribution on a histogram once again. Okay, now if you notice, if we take a look at this, they're literally the exact same thing. All I did was move everything down. This used to be at 900, now it's at 800. This used to be at 750, now it's at 650. Literally, all I did was take this histogram and shift it down 100. So the amount of money that he makes to get the profit by subtracting 100 is I just took this whole histogram and shifted it down. The mean then was 562.50. Since I moved it down my number line, that means the new mean's also going to move down the number line, which makes it 462.50. But take a look at the standard deviation. The standard deviation is still the same. Well, why is it still the same? I'm not changing how far spread out the data is. I'm physically just taking this, moving it down the number line, and plopping it back. The spread has not changed at all. Okay, so to get the new mean, I take the old mean, subtract 100, get my new mean because I shifted it down the number line. The old standard deviation is the exact same as the new standard deviation because my data has not changed the spread at all. Okay, I've just literally moved it down the number line, looks exactly the same. Now, why did the mean change but not the standard deviation? Every x value on the graph was shifted down 100, therefore the mean is going to move with the graph down 100. Since the whole graph shifted to the left, the spread didn't change, therefore the standard deviation did not change at all. Okay, so if we were going to just take a look at comparing the mean and the standard deviation, the shape, when we add or subtract a constant, stays the same. The two probability distributions have the same shape. They're both approximately normal. Just make sure to remember when you're doing this that you're using comparative language. The mean is 562 and the mean of the profit is 462, which means the mean of the profit is the old mean minus 100. The standard deviation of the cost is the same as the standard deviation of the profit, which means they're exactly the